Section 4.11, Lattice Enthalpy and the Bourne-Haber cycle. First, let's look at this table of lattice enthalpies of some simple ionic compounds. So let's look for the smallest numbers and also the largest numbers. So these are the smallest numbers, 600-ish. These two are the largest numbers, around 10,000. So now let's compare these two different kind of ionic compounds. Over here you have only plus 1 charge on cesium, only minus 1 charge on iodine. Over here you have plus 4 charge on titanium and minus 2 charge on oxide. Therefore, we can tell if we have very large charges on the cations and also on the anions, we will have large electrostatic attraction and therefore large lattice enthalpy. When we have smaller charges, we have smaller lattice enthalpy. After all, the electrostatic attraction is Z plus times Z minus over the distance between the two ions. So if we have a large Z plus, a large Z minus, and then we will have very large lattice enthalpies, like in these two cases. Again, in these two cases, we have very large plus 4 charge on the cations and fairly large minus 2 charge on the anions. And on here, cesium iodide, cesium bromide, we have only plus 1 and minus 1 charges. And also, if you compare these two compounds, cesium fluoride, chloride, bromide, and iodide, realize this: fluoride is smaller than chloride, smaller than bromide, bromide is smaller than iodide. And then we know the distance between this cesium plus and this fluoride is smaller than that in cesium chloride, than cesium bromide, than cesium iodide. And therefore we predict this enthalpy is greater than this one, greater than this one, greater than this one. Only because, again, if we look at the distance, these two are closer to each other, and then we have a larger lattice enthalpy. So in general, we look at the charges, we look at the distance between the cation and anion. And now let's look at a few other examples. If we compare this lithium fluoride versus this sodium fluoride. This lithium fluoride has a larger lattice enthalpy than sodium fluoride. So if you compare the charges, they're the same. So really it depends on the distance. The distance between lithium plus and fluorine minus is smaller than the distance between sodium plus and fluorine minus. Now let's look at a typical Bourne-Haber cycle here. How do we determine this enthalpy lattice? Well, it's very simple. We learned Hess's law. It tells us this enthalpy is a state function. So if we like to determine the change of the enthalpy, we can design different processes as long as they have the same initial state and the same final state. Then the entropy change is going to be exactly the same. So right here, let's look at this Bourne-Haber cycle. So this is potassium chloride solid. This is an ionic compound. So from here to here, from separate potassium plus ions and chlorine minus ions to this ionic compound, we have this unknown X here. This X is the lattice enthalpy. But how do we determine this? Well, somehow we can combust potassium in chlorine gas. We can form KCl. We can measure the enthalpy of the enthalpy change of this reaction. And also from here to here, this is the sublimation of potassium. We can measure the enthalpy change of this process as well. And from here to over here, well, that's just the ionization energy of potassium. From here to here, well, that's the decomposition of this chlorine molecule, from molecule to chlorine atom. And then from here to here, this is simply the electron affinity of chlorine. So if we can somehow determine this number, this number, this number, this number, and this number, and then we know that all these numbers all these numbers plus this number should be 0. Again, this is a cyclic process. So if we sum up all these numbers, the result should be 0. So how do we determine this x? It's going to be very simple. It's going to be this number plus this number plus this number plus this number, the sum of these 4 numbers, and then subtract 355. We get this segment. That's the lattice enthalpy of potassium chloride. And of course, you can draw this cycle for any other ionic compounds. Now let's look at this Madelon constant. What does that mean? If we have a sodium chloride ionic compound or any other ionic compound with this rock salt structure, and then let's focus on this ion. Let's say this is just ion 0, all right? And it's surrounded by 6 neighboring counter ions labeled by 1. 1, 1, 1, 1, 1, 1. All right, 6 of them with a distance. Let's say this is just d. This distance is d. So how can we calculate the electrostatic attraction between this ion 0 and the 6 ions 1? Very simple. It's going to be 6 times this charge times this charge over the distance d, right? So again, if we're talking about sodium chloride, the simplest case, the charge on sodium plus and chlorine minus is +1 and -1. And then we'll just use +1 and -1 in the formula for calculating the electrostatic attraction. All right? So it's going to be, let's say this is sodium, okay? Let's say this is sodium, and then this is chlorine. And then the attraction between these two is simply +1 times -1 over the distance d. All right? But there are 6 of them. So it's going to be 6 times +1 times -1 over d. So you have -6 over here. All right? That's the first term. This is the attraction between this ion and its 6 surrounding counter ions. All right, but don't forget this. This ion is repelled by this type 2 ions. The type 2 ions, labeled by number 2, is the second layer surrounding this ion. And this type 2 ions repel this ion. So how many are there? I think there are 12. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There should be another one over here. I forgot to count this one. So again, there are 2 on top. 1, 2, 3, 4. There's 4 on top. There are 4 in the same plane with this one. There are 4 below this ion. So there are a total of 12. That's why we have 12 here. Okay, and we have a positive sign here because this type 2 and this type 0, they have the same charge. Divided by square root of 2. Why is that? Well, it's very simple. If the distance between 0 and 1 is d, then the distance between 0 and 2 is the square root of 2d. So this square root of 2 takes the longer distance into account. And then minus 8 over square root of 3. When you see minus, that means, well, we're looking for counter ions. So let's look for type 3. So this type 0 is surrounded by 8 type 3 ions with opposite charges. What are those 3? Okay, this is type 0 in the center. 1, 2, 3, 4, and then 5, 6, 7, 8. 8 of them, therefore, we have this number 8 here. It's a negative sign because we have opposite charges. And then finally, over square root of 3. Why is that? Okay, again, from 0 to 3. This is from corner to corner diagonal of a cube. And the distance between this 0 and 3 is square root of 3 times this lattice constant, or the silence of the cube. That's why. And then we keep going. You will see we keep going. And then we have infinite series. If you sum up all those numbers, you will get negative 1.748. This is the Madelung constant for this rock salt structure. And again, you see this number here for rock salt structure. The symbol is A in the textbook, but it's M in this Wikipedia page for this Madelung constant. But again, I mean, this is a Madelung, so I think it's more natural to use M, but unfortunately in the textbook, A is the symbol for the Madelung constant, 1.748. For other structures, of course, you have different structures, and then you have different Madelung constant.